Hello everyone, my name is Gjorgi Peev. The topic of today's talk is aiding the task of process-based modeling with ProbModVis. This work was done with the collaboration of Dr. Nikola Simijievski and Professor Dr. Sasha Jerovsky. Process-based modeling is an equation discovery approach for automated modeling of dynamical systems. In the process-based modeling formalism, the output process-based models are represented at two levels. At the high level, they are represented as modeling components, entities and processes. The entities represent the actors of the system, and the processes represent the actions those actors do. At the lower level, these components are translated into a set of equations, most commonly ordinary differential equations, which are comprehensible and which represent some physical laws. ProbMod is the latest software implementation of the process-based modeling approach, and it has been really successful in the tasks of modeling dynamical systems. However, it has some usability limitations and narrow user base. The reason for that is because the output process-based models are not really comprehensible for a broader user base, and it's not really user-friendly. So our proposal is ProbModVis, which is a software platform consisting of a graphical user interface for ProbMod and a visualizer for the output process-based models. With that, we'll facilitate the task of process-based modeling and we'll make ProbMod more user-friendly, and we'll give the output process-based models a graphical representations which will make them more comprehensible. So our problem is defined as follows. This is ProbMod's workflow. In order to start ProbMod, we need several input files, which we need to prepare. The library of domain knowledge, which specifies the domain from the system to be modeled is in. Then we have conceptual model, which specifies the particular problem. And then we have task specifications and data, which specify the particular task we want to execute. This is the current representation of these input files. It's textual and it's kind of confusing, but the most difficulties that the user have is with the task specification file. It's an XML file, and it consists of all the hyperparameters needed for ProbMod in order to run smoothly, like the paths to the other input files, the mappings of the endogenous and exogenous variables to some particular columns in a data set, defining of inputs and outputs, and also the simulator filter settings, etc. So this is the most cumbersome file for the users to create, and that's why we introduced ProbModVis, where and especially the ProbMod GUI part, where this is encapsulated in one shell, let's say. So it's an intuitive platform that guides the user step by step in creating the process-based modeling task. And then it also offers analysis tools at the output, and also we can have the ProbMod visualizer is at the end, where we can visualize the output process-based models. The graphical user interface looks like this. There are a few screenshots of it. It's consisted of 9 main scenes which guide, as I said, the user step by step in order to create the process-based modeling task. We first have to choose the library and the incomplete model, where we can see all of their components, then the data file where we can visualize the data and then specify the input and the outputs and map them to a particular column in the data set. And then we should specify the settings, like the simulator, the filter settings, and this is all done interactively, and it's really intuitive. It results with, while ProbMod searches through the search space, it results with candidate models, and we can inspect them while ProbMod still searches for other candidate models. We can visualize their simulation, evaluation, and we can also view their visual model and also the textual model. So how does a visual model in ProbMod looks like? As I said, the two main components are the processes and entities. So we have two main components, and the influence of a process to an entity or participation of an entity in a process is represented with a gray arrow from one to another. However, they also can have subcomponents, which are the hierarchical templates of entities and also of processes. Processes can also have nested instant processes in their definition. So this is the full schematics of a visual process-based model. In order to better illustrate all of that and the use of ProbMod Vis, we are going to have two case studies. We'll model two nonlinear dynamical benchmark systems, which are two cascaded water tanks and the silver box, which is an oscillator system. We measure their performance according to their relative root mean square error. The two cascaded water tank system is shown in this picture. It's consisted of two water tanks placed one above the other with three outlets fed, and they are fed by a pump. So the ground truth or the behavior of this particular model is represented at this picture, and there we can see that we have inflow from the pump to the upper tank, we have flow from the upper to the lower tank, and outflow from the lower tank. And that behavior is squared root behavior of H1 and H2. Our task is to model the behavior of the lower tank, and also in the process-based modeling library we encode some alternatives, some additional behaviors of H1 and H2 which are linear and exponential. The experimental setup consists of the data is as follows. The data set is consisted of 2,500 samples from laboratory measurements split into a train and a test set of the input signal, which is the voltage applied to the pump, and the two output signals, which are the water height level in both of the tanks. This is how it looks like in the ProbMod GUI. As we can see in the library, we have defined the three behaviors of the water, the square root linear and exponential behavior of the inflow, outflow, and the unit and the mutual flow between two tanks. And we define our particular task. We say that it's consisted of two tanks and one pump, and we don't know the particular behavior. With defining the simulator and the filter settings, it results with 9 model structures, which are all combinations of the all possible behaviors. As you can see, the best results are obtained with the model consisting of the two square root behaviors, which in fact is our system. This is how the visual model looks like. We can see that we have inflow from the pump to the upper tank, and then we have flow with the square root behavior from the upper to the lower tank, and outflow with square root behavior from the lower tank. This is a plot, a comparison between the measured and the predicted value of the water height level in the lower tank. The second case study is the silver box, which is an oscillator system. In our library, we encode the ground truth behavior of this system, which is a Duffing oscillator, and then we have 3 more oscillators, simple, harmonic, and universal oscillators. This is the experimental setup of 130,000 samples split into a train and a test set of the input and the output signal. This is how it looks like in the GUI. We can see the encoded different behaviors, and in our particular system we say that we have an oscillator with unknown behavior. So it results with 4 models, out of which the best results are obtained with the Duffing oscillator, which in fact is our system at hand. This is how it looks like. We can see that we have input voltage to the oscillator, it's initialized, and it has some Duffing oscillator behavior. This is the plot between the measured and simulated value of the output displacement of the oscillator. So we can conclude that we've designed and implemented a new platform, ProbMod Vis, which is useful in aiding the task of process-based modeling. It's consisted of GUI for ProbMod and process-based model visualizer. With ProbModWiz, we facilitate the task of process-based modeling. We normalize the process of task specification in ProbMod, and all of this is evaluated with modeling to benchmark systems for nonlinear system identification. That was it, so if you have any questions, and you can see more on the website for probmod.ijs.c.
So, any questions?
I was wondering what the main or expert knowledge, I'm not sure how you called it, was in these two cases.
Could you just repeat the question for the recording, please?
The how much main or expert knowledge was in the two case studies. There weren't big libraries. For example, in the water tanks system library, we had the behavior of, as I said, inflow from a pump to a tank, and then we had flow between two tanks and three alternatives of it: square root behavior, linear, and exponential. And the same goes with the outflow from one tank, and we had linear, exponential, and square root behavior of it.
So the type of models.
Yeah.
Another question. This graphical interface, can you do everything that XML representation can, or is it limited in some way?
No, it can do everything that the XML represent.
Okay.